All right. Let's see what this looks like. Not bad. So friends, I think I'm going to lose the desire I had to have 10,000 trials for you. At some point during the break, the computer turned itself off. So I restarted it. But I don't think we've lost anything. I mean, we've lost our 10,000 trials, which sucks. But check this out. At this point, I just stopped it right around 1,000 or so. Around 1,000 or so. You can look at the distribution that we have right now, which is loosely tied to our theoretical distribution. 1 in 36, just about 3%. 2 in 36, just about 5%. 3 in 36, just about 9%. They're off by a percentage up or down, but they're damn close. 6 in 36 for 7, 17%, which is perfect to 2 decimals. You can look at that distribution and say, what are the unusual outcomes? What are the unusual outcomes? Now you could do it the 2 standard deviation way, which is perfect. Average, plus or minus 2 standard deviations. There's typical, that means that's unusual. You can do it that way, or you can just look at the probabilities and say, oh look, we're hardly ever getting 2s, and we're hardly ever getting 12s. When I say hardly ever, what am I using as a metric to measure this? I'm using probabilities less than 5%. That comes in at 3%, that comes in at 3%. Those are the ones that happen rarely. Since they happen rarely, we call those outliers. That's all. That's all. And Haley, you asked a great question earlier about the difference between this range of data, setting up the outliers, and looking at these numbers to separate the outliers. Fantastic question for me to think about pedagogically. Is that fair? Fairish, fairish. Okay, good. So that's another way of looking at identifying the likelihood or non-likelihood of individual events. What I want to take the rest of the class time to do is to actually look at how to use this in a gambling/insurance methodology. And this is where it really crosses into your lives. Yeah, rolling 2 dice is great. You're playing board games or whatever, and that's fantastic. But when you think about the idea of the average of this distribution, it actually has quite a bit of application. Here's a Vegas application. Let me turn over to here. There's a game called Chuck-a-Luck, okay? So here's the rules of Chuck-a-Luck. I'll have these posted for you later if you, let's see if I can, how do I zoom? This is all new to me. Zoom, here we go. Zoom out. Thanks, I am zoomed out all the way. Oh. Okay, so I'm going to zoom out the old school way by lifting this up. There we go. Chuck-a-Luck. So Chuck-a-Luck is a pretty basic, it's a fairly basic gambling game. It involves 3 dice. Put in this thing called a bird cage. And you actually, before you do anything, you pay to play. You walk up and put $1 down. Put $1 on the table, say I bet $1 to play this game. Spin the bird cage. And then what happens next is your dollar is attached to one of 6 numbers. So you might put your dollar on 5. And what you're essentially doing is you're betting on 5. You're betting that 5 will come up. And here are the rules. If 5 comes up on none of the dice at all, you lose your dollar. They take it away from you. If 5 comes up on one of the 3 dice, you get your dollar back. They give you $1 for playing, and that means you've broken even and you've gotten nothing. If 5 comes up on 2 of the dice, they give you $2 back, which means now you're ahead by 1. And if 5 comes up on all 3 of them, they give you $10 back. $10 back, which means you've got $9 more than when you started. $10 back. So basically 10 to 1 odds. What I'm giving you is the odds. If you get all 3 of them you bet on, you get 10 times back what you bet. So if you bet $10, they'll give you 100. But I'm just going with a bet of $1. Right. So what I want to do is I want to analyze this game. All right? So Chuck-a-Luck has a beautiful little mathematical pattern here. But what I want to do is I want to find out on average how much we're going to lose. Because you know we're going to lose on average. It's a gambling game. So I'm going to mute this down real quick. Mute this down. We're going to analyze this game. Okay? So, example 3, Chuck-a-Luck. And all gambling games are basically going to follow this kind of argument with varying probabilities. Craps, for example, is a little too involved to deal with in this class at this time, although I'd like to deal with it later on in class if we have more time. So what I'm interested in now is, essentially, I'm going to define my random variable to be how much I win. How much I win. I'm going to put win in quotes because you're not always going to win anything. Sometimes you're going to lose. And then in the right column, I'm going to put what's the chance of winning that much money. So how much am I going to win in the left column? And then on the right column, what's the chance of winning that much money? Now what I want to do is, I'm going to put a little column off to the left here, which is going to help me keep track of how much I win by virtue of what happens during the game. So I'm going to put number of fives that I roll. This isn't actually part of the distribution, but it's going to help me decide. It's going to help me decide how much I can actually take in over there. So if I bet on 5, I'm choosing to bet on 5. Does it matter if I bet on 6 or bet on 4 or bet on 3? It's all the same. So I picked at random the number 5. How many 5s could I theoretically roll?
3.
All 3? What else? 1, 2,
Or none.
or none.
Yeah.
So really, the number of 5s goes 0, 1, 2, 3. The number of 5s goes 0, 1, 2, and 3. If I roll no 5s and I bet on 5, how much do I win?
Nothing.
Actually, technically, you lose $1 each. You're actually -1, aren't you?
Yep.
You're in the hole $1 because you bet $1 to play. Does that make sense? You bet $1 to play, which is kind of an annoyance. If you bet on 5 and you roll 1 5. Now, when I say you roll 1 5, that means the other two came up like 6 and 4. So 4, 5, 6, or 1, 2, 5, or something like that. What do you win now?
Nothing.
You actually do win nothing there, don't you? That's breaking even. Because you bet $1 on your ante, but you also got $1 back, so you cut your losses to 0. What if you get 2? What do you win now? You actually win $1. You bet 2 to 1 odds. So you bet $1, they give you $2 back, you actually get paid $1 extra for what you bet. And if you win 3, jackpot, you actually end up making 9 because we have to offset. Right, it's 10 to 1 odds, Jimmy. You got that. It's 10 to 1 odds. But you have to offset the 10 to 1 odds by the fact you bet $1 to play. So you clear 9. Those are our random variables. Those are the actual, I know these are 2, but you don't win the pips on your dice. You win the actual dollar amounts associated with that, with those pips. So now the question is, what goes here? Which outcome do you think is the most common? Which outcome do you think is the most common? 0, I vote for 0 5s, most common? Which is the least common, do you think? Oh, okay, good. So the most common would probably be 1 out of 1 5. Good. So you vote for 1, 1 0, maybe somewhere between. I like that too. Very good, very good. Jenny, what are you thinking?
I was going to say 1, yeah.
Yeah. So obviously you guys are thinking these probably aren't the most common outcomes, right? Now that would make perfect sense, wouldn't it? For a number of reasons. Number 1, they're actually paying you for those. Vegas isn't going to pay you. They're not going to pay you, right? They're not going to pay you for coming into their casino. They're going to take your money away from you, which is how they keep their casinos open all the time. So the idea is, which of these is the most likely outcome? Well, let's figure it out. Let's figure it out. Now, I'm going to simulate this one, and then we're going to revisit it later on. Rob was talking about having formulas to generate these kinds of probabilities. There is a formula for this, but whenever I tried coming at this one right now with a formula, it backfires in my face. So for right now, please accept a simulation to get those probabilities with a promise that we'll go back to it within a week or so. Okay? Let me switch over to the computer to make sure it's still working. Okay, working. Good. Goodbye, beautiful dice. Yes, I know you have. Chuckle. So what you're going to see here, it's the same thing as you just saw in the other one, but I'm rolling 5s over here. Here's your dice. So if I press F9, right now I have no 5s at all. Right now I've got no 5s at all, no 5s at all, no 5s at all. There's 2 5s. Okay, so we're keeping track of that right here. And this is all that's going on is I'm using Excel just like I use your TI when you use that randint command. Same exact thing, except I've got the dice actually showing there. So what I'm going to do is I'm going to go ahead and let this thing run, and let's see what kind of a distribution we get. Let's see what kind of a distribution we get. Let's see what kind of a distribution.
How's this game illegal?
Was that? Say that again?
How's this game illegal?
Because they don't force you to walk into the casino.
Right.
Right.
Right? They don't force you to walk in there.
They don't
You
have
go in there
to.
on your own accord. They don't force you to stay.
Yeah.
But they give you free drinks. Right? They give you free drinks.
And this is
Mimosas, right?
Adrenaline.
Right, and the adrenaline, all the lights beeping and all that. Right. So you're looking, and the first thing Robin says is, how is it even legal? Because she's looking up there and she's realizing, look at this. Yeah, that's the jackpot, right?
Yeah.
Happening 5, 6, 7. It's going up.
Look,
Kidding. Right, exactly. And Elena's looking over here. Now, every once in a while, there's a 2 that jumps in. There's a 2, and then 2. But how many 3s are we seeing?
No.
Very, very few 3s. I mean, here's the total number of 3s we've seen in 1,700 trials.
So does that mean that you lost like $1,000 or whatever?
I love this. Can we go back to that question in 2 minutes, Jada? I love that question, and I want to come back to it just momentarily. And you guys can tell me. Now, please notice, that these are pretty much hovering where they are now. They pretty much stabilized at their probabilities at this point. This is looking like 57, 58%. This is looking like 34, 35%. That's looking about 7%. That's looking pretty crappy. About 0.5%, right? So I think we could probably pull the plug on this and just use those numbers, yes?
Yeah.
Let's go ahead and do that. So let's go ahead and just stop this guy. Let's use those values right there. Let's add those to our distribution.
Okay.
You have about a 58% chance. 50, you know what, let's go to 5.7, actually it'll be 58, 0.58. This guy right here is about 0.343. This guy here is about 0.073. And this guy here is pretty lame, 0.005. I love the question Jada just asked. I'm going to mute the screen down. Thank you, Excel, for behaving one last time for us. Jada's question is fantastic. Because the question is, on average, how much do, that's a U, I think. I think it's a U. How much do we win at Chuck-a-Luck?
So we have a 58% chance of being -1.
Good. I love this. I love this, Jenny. Thank you. I'm going to slide over here so we can see this. Yes, we have, you hear what Jenny just said? We have a 58% chance of losing $1. But we also have what?
34
We have a 34% chance
of not even
of breaking even. And we also have a
7% chance.
7.3% chance of gaining $1. And we've got a 0.5%, 1/2% chance of winning big. Winning big. I almost said losing. Winning big and winning not. So the question is, how do we find the average of this? And you know the answer from half this class ago. What kind of average am I asking you to find? It starts with a W. It's a weighted average. You have to, this is your data, -1, 0, 1, and 9, and you apply these weights to it and sum them all together. You guys just, what you just said, there's a 58% chance of losing $1. Of in mathematics means times. Now, we use our TIs generally to do this. I mean, I think we should continue to use our TIs to do it. But the basic idea, I'm going to write it out one more time before we default to our TIs and do this for us. But what you guys just said, there's a 58% chance of losing $1. There's also a 34.3% chance of breaking even. That becomes 0 anyway. There's also a 7.3% chance of winning $1. And last but not least, don't forget, there's a 1.5% chance that you win 9. And what you're doing when you calculate this weighted average is you're adding up all the components to your, if you will, win. You're adding up all the components to your win. That's what you're seeing right here in this computation. The -1s only get contributed about 60% of the time. The 0s get contributed about a third of the time. The 1 gets contributed about 7/100ths of the time, and you hardly ever see the 9 pop up. But that's how they get you right there. 10-to-1 payout! Yes, but it happens that frequently, but nobody pays attention to that. Or they selectively ignore that. Shall we calculate? Yeah, shall we calculate? Actually, do you want to just crunch it out like that since it's already written out? Instead of using one of our stats, let's just do this. You know what? Let's not do one of our stats, because one of our stats is also going to give us a standard deviation, isn't it? And should I even look at that standard deviation on this data? No. Not really. It's not bell-shaped. It's unimodal, but it's definitely horrendous. So let's fire this up. Let's fire this bad boy up over here. Dr. Cam. Did that work? Oh, goodness. Yes, it did. Okay.
And you said that's a 9 somewhere?
That's a 9 down where?
At the end? Your-
Oh yeah, that's just a 9. Yep, because you get $10 get back to you, but you lost $1 to play. So we've got 0.58 times a -1 plus 0.343 times 0 plus 0.073 times 1 plus 0.005. Oh, make sure you use a negative and not a subtraction sign. I guarantee that's what's going on. There,
Thank
let me just take a look.
Yeah.
Yep, right there. Just change that to a negative sign. All right, friends, you ready? What does this mean?
You know what?
What does this mean?
Okay.
What does it mean?
There's 46 cents.
So, on
Whatever.
average, can you actually lose 46 cents playing this game at any one time?
No.
You can't. You're either going to lose $1,
Yeah.
break even, win $1, or win $10, or win $9, I guess. You can't actually lose 46 cents, but you can what? What is the negative 46 cents again?
That's
It's an average loss. Average loss. So essentially, here's the deal. Every time you walk up to this table and you hand them $1, instead of actually handing them $1, you could go in and argue and just hand them 46 cents and say, I'm not going to play. Here's 46 cents and I'm going to walk away. Because on average, that's what's going to happen anyway, right? Of course, they'll never agree with that.
That's what, I'm thinking about a huge big poster, in front of.
Oh, they don't want
No,
that.
no.
Oh God, that's like putting that nutrition information in McDonald's. Notice how it's in 8-point font on the side near the bathroom. You're not going to see it, right? Exactly. You don't want, Vegas doesn't want this kind of crap known. Please realize too, friends, and so that you can, I'm not telling you not to gamble, okay? I'm telling you, if you want to go to Vegas, have a good time. Just realize what you're getting in for. Don't treat gambling as investment, all right? This is what you're in. And this makes perfect sense because a loss of 46 cents for you equates to a gain of 46 cents to them. You lost the 46 cents. Basically, your dollar became 54 cents. Exactly. The other 46 went to Vegas because you're losing that. Yeah, you got it, Dave. That's the problem. That's the problem with it. Cool? Makes,
per every dollar.
for every game you play, you lose 46 cents. Exactly. So per dollar played, it equates to an average loss of 46. It can't be an average loss of $1 because every once in a blue moon you do win money, right? Every once in a blue moon you do gain some money back. I mean, 0.005 times 9 is $0.45, correct? I'm doing my math right. It's 0.045. It's 4.5 cents. So every time, right? But think about that. That gets added into the negative and makes it less negative. Same as this. This is 7.3 cents. So you add the 7.3 cents to that 0.045 cents over here, and that ends up contributing back into the negative that's over here. It's still not positive. Still not positive. But it still takes away from some of that negative bite that this guy over here, this is negative 58 cents. The other 8 or so cents that offsets that is over here. So yeah, and they can mess with that. They can say, you know what? You know what we're going to do next? We're going to make the payout 20 to 1. Make the payout 20 to 1. In other words, this won't be 9 anymore. It'll be 19. Well, yeah, that's fantastic. It sounds fantastic, doesn't it? But all that's going to do is increase this by a little tiny amount, which is going to decrease that by a little tiny amount. So now you're negative 43 instead of negative 46. But 20 to 1 payouts.
Yeah.
20 to 1 payouts. 30 to 1 payouts. 40 to 1 payout. That's the problem. That's the problem. Cool?
Yeah.
Now, as much as I love gambling, and it is pretty wonderful, especially when you understand it, I want to show you how it applies to your life in a less Vegas-y, Reno-y kind of way, casino-y kind of way. And I want to talk about insurance. So what I've got is I've got an in-class quiz for us to kind of slow through. I couldn't resist some more gambling at the bottom. Yeah, play that too if you want. But I want us to spend the rest of the time together with this right here. And the reason I like this is because everything we just did today and yesterday, the rolling a single die, the rolling 2 dice, the rolling 3 dice, which essentially we just did right now, a lot of it is based in the theoretical of what can happen when you actually throw these physical objects. I know we kind of cheated with Chuck-a-Luck because I didn't actually throw 3 dice. I actually threw 3 dice using Excel. But these distributions in here are actually created from statistical tables that actuaries have put together, which is a way more useful for you guys. So everybody go ahead. If you want to pair up with somebody, that's totally fine too. Here we go, hand these back. If you want to pair up, just have everybody put their name on one quiz. Let me shut this down.